Okay, so hello again, and it's the fourth part of the series on combinatorics of Young, tableau, and symmetric groups by Sarah Whitehouse from Sheffield. So please, Sarah.
Thank you very much. So welcome back, everybody. Yeah, so this is lecture 4 of this mini course, and this is the final lecture. We have another session, the 5th session tomorrow morning for this mini course, but that's going to be a question and answer session. So this is the sort of final prepared lecture. Do please have a think about what you might like to ask me to do with that hour tomorrow morning. I haven't prepared material to present, but I'm really happy to take all kinds of questions or requests. So it could be requests to go back over bits of the material I've presented, or obviously questions arising from that. And then another thing we could do is look at the problem sheet and problems from there, and you can make requests of particular problems from the problem sheet if you want. I have written solutions, and you'll get solutions after the end of the mini course. So probably later tomorrow or something, you'll have solutions to the problems anyway, but we might want to spend some of the time going over some of those. So yeah, have a think about it, and then maybe we can start tomorrow morning with people putting requests in the chat, and I'll just see what comes up and how we use the time. Okay, so what am I going to do in this last lecture then? Well, let me start with start with an overview of the 3 lectures that we've had so far then. So this is going to be very brief, but just to remind you what I've done so far. Well, at the very beginning, we saw some stuff about the symmetric group, and we're coming back to that in this lecture. But then after that, we've seen a whole bunch of combinatorial objects. We talked about partitions, about Young diagrams, Young tableau, and especially about standard Young tableau. So I won't remind you exactly what those are, although we'll see them again later in this lecture anyway. But remember what we did with this. Well, first we had some notation, f lambda, for the number of standard Young tableau of shape lambda. So here we've fixed a natural number n, and we've fixed a lambda, which is a partition of n, and we thought about the number of standard Young tableau of shape lambda, and we called that f lambda. And what I was doing in the last lecture this morning was talking about the hook formula and sketching some of the ingredients that go into a bijective proof of the hook formula. So here's a reminder of what the hook formula was. So we had formula for the number of standard Young tableau of shape lambda of the form n factorial divided by the product of the hook lengths. And in the previous lecture, I'd also talked about a different formula for the same thing in the form of a determinant, or involving a determinant, and I showed you that those 2 formulas are indeed equal to each other. So that's a summary of where we've got to so far. And this lecture is an attempt to answer the question of who cares. So why should we care about the number of standard Young tableau? I mean, you know, so these are just some combinatorial kind of thing that, well, I was about to say I've invented, but I certainly haven't. I guess Alfred Young was the first person to think about these particular combinatorial objects. But you might ask, why would you do so? And what, we can define all kinds of finite sets and then try to count how many elements there are, but generally we have to have some good reason for bothering to do so. So why should we care about this particular counting problem that we've seen solved in the previous lectures? So I think there are some different answers to this question, but there's one main one, or at least one which I actually understand, and which is sort of the reason that I might care about this. And so I'll present in this lecture one answer to the question, and then hopefully enough background and details about it to explain what the answer means, given that when I first put up the answer, you probably won't understand a lot of the words in it. So here's an answer, but I'm not expecting you to understand it. I'm hoping to give you some insight into what it means by the end of this lecture. So the statement is that this f lambda is equal to the dimension of some irreducible representation, something called S lambda, some other thing, of the symmetric group Sn, and this is the particular one associated to a partition lambda of n. So, I mean, the words on the second line of this statement mean something to you, I hope, from the previous lectures. So most people probably met the symmetric group before, or if you didn't, you met it in the first of my lectures. So you know about the symmetric group as a group of permutations, and then I've been talking for several lectures now about partitions of n. So the second line here sort of makes sense. You know what the symmetric group is, you know what partition lambda of n means, and on the other hand, I'm not expecting the things on the first line to mean very much, and I want to spend this lecture trying to explain what they mean. So, and I mean, this will not be in a great deal of detail, but I want to get some ideas across enough for you to have some idea of what this means and why it might be important. Okay, so let's try and explain some of the words on that first line, just very roughly, firstly, and then I'll go on to explain them in more detail mathematically. So let's start with this word representation. So that's the key thing that we need to understand. What does it mean to have a representation of a group? So a representation of a group, well, very loosely, it's an object on which the group acts. So in this case, our focus is on symmetric group, Sn, and we're interested in something, an object. In fact, it will be a vector space, but just some object on which the group acts. So, you know, all kinds of objects have symmetries, and those are captured by, or very often, an action of the symmetric group. And we want to be able to study those objects and have a theory that kind of tells you what's going on in terms of group actions. So this is what representation theory does, representation theory of groups. And because the objects which a group acts on, the ones we're going to look at, are vector spaces, they'll be finite dimensional vector spaces. So actually, if you've done a little bit of linear algebra, you do actually know what the word dimension means here. It means what you think it means. It's going to be the dimension of some finite dimensional vector space. So if you've done some linear algebra, you will have seen that notion of dimension. If you haven't, it's a measure of size. Okay, and then the other word that I haven't said anything about yet is irreducible. That's said here towards the bottom of the slide. So we have a representation, some kind of object, vector space on which the group acts. And an irreducible one, well, it's kind of what it sounds like. It's one which doesn't have any kind of non-trivial smaller pieces. So it's one that can't be broken down, if you like, into smaller parts. So whatever these things really are, these irreducible representations of the symmetric group, they're the basic building blocks for understanding all symmetries, all actions of the symmetric group, because every object, vector space, on which the group acts, it can be expressed in terms of these basic building blocks. You can sort of express a general one as a sum of pieces which are given by these irreducible ones. So if you can understand these basic building blocks, you can build everything else from them, and you can understand all these actions. So that was extremely vague, but it was an attempt to give some intuition for what representations are and what these irreducible ones are. So I'm going to say more. I'm going to tell you properly what a representation is. I won't tell you properly about irreducible just for reasons of time, but you have enough for sort of intuition about them being the basic building blocks. And the point anyway is that you should think of this statement up here as, well, giving one answer to why the F lambdas are important, and at least connecting up the sort of combinatorial material that I've been talking about for 2.5 lectures with what I started with about symmetric groups and permutations, because it's explaining, you know, what the role of, or one of the roles of partitions, and we will see in a moment also tableau and standard tableau, what they have to do with permutations and the symmetric group. So it's connecting up all these things. Okay, so let me tell you what a group representation is then. And I might as well tell you for a general finite group, because it works just the same for any general finite group, although the ones we're really interested in here are the symmetric groups. So let G be a finite group, and let's call its identity element E, just because I need a name for that in a moment. So I said that the objects the group acts on, they're going to be vector spaces. So I'm going to give myself a finite dimensional complex vector space V. And the representations that I'm talking about then are finite dimensional complex, because I made those choices of finite dimensional vector spaces and complex vector spaces. You could make other choices, but, well, if you do infinite dimensional things, then the kind of theory, the standard theory that you might want to think about doesn't really work. And if you can work with other fields, not necessarily the complex numbers, but the complex numbers is the sort of simplest and most straightforward thing to do. Anyway, it doesn't really matter, but let's do finite dimensional vector spaces over the complex numbers. Okay, so what we want is one of those, and I'm sort of hoping that you've seen a little bit of linear algebra and you know what this means. I mean, you can just think about sort of Cn, the sort of standard view of complex n-dimensional space, and that's fine. And then we don't want just a vector space, we want one together with an action of our fixed finite group G. And let me just tell you what it actually means to have an action of a group on a vector space. So, I mean, what it means is that if you pick a group element little g and a vector in the vector space, then you have assigned another vector in the vector space, which is what you get when you act on V by G. So a group element acts on a vector and gives you another vector, or possibly the same one, but takes vectors to vectors. That's the nature of an action of G. So for each element of the group and each vector, you have specified another vector, which is written GV for G acting on the vector V. And you have to have some compatibility conditions between the group structure and the vector space structure. So this thing, vector space with action of a group, it's putting together a vector space and a group, and you would expect some axioms for that to be reasonable. Compatibility, as I say, between the group structure and the vector space structure. So one thing that you would expect is that the identity element of the group should act as the identity. So if you act on a vector by the identity element in the group, then it shouldn't change. So EV is V. This is true for all V in the vector space. Then you should have a compatibility of the action of the group with the multiplication within the group. And that's what's written in this bullet point here. So let's maybe start on the right-hand side. So if I take the vector V and act on it by a group element H and then by another group element G, that should be the same as first performing the corresponding multiplication of G and H in the group and then making that element of the group act. So that's saying that action is compatible with the group multiplication. And I guess maybe I didn't say it, but my finite group, I'm writing the group operation as sort of multiplication silently by just putting group elements next to each other. Okay, and then finally, there's another thing which says that the action should be compatible with the vector space structure of V. Or another way to say it would be to say that each element of the group should act linearly on the vector space. And that's what's expressed in this final bullet point of the definition of an action. So G acts on a linear combination alpha V plus beta W, sending it to alpha G of V plus beta G of W. So it's respecting the addition and the scalar multiplication of the vector space. In other words, it's acting linearly. So this is the definition of a group action on a finite dimensional complex vector space, and that is what a finite dimensional complex representation of a group is. It's such a vector space with an action with these compatibility conditions. And obviously the vector space has a dimension, and you would also call that the dimension of the representation. So that's something that I mentioned earlier. Yeah, and someone said, so an action is a group homomorphism. Yes, you can express it that way. And in fact, there's lots of different ways to formulate the definition of representation. So for those who know about the general linear group and so on, you could say it that way. You could say that it's a homomorphism from the group G to the general linear group of linear transformations of the vector space B. And there are other ways you can formulate it as well. But yeah, so some of these things, like the linearity, you could capture that in a more slick way. For example, like I just said it, but I wanted to like write it out longhand so that people can see what it means. So I wasn't going for the most slick way of saying it. And then there's another question: does the non-complex version of this use modules? Yes, that's right. So if people know about modules, then you can formulate it as well with modules. You could formulate the complex one with modules. It's just that because there you're working over a field, you know, a module happens to be a vector space. But yeah, so if you were to work over a ring that's not a field, then you could say this in terms of modules over the ring, and indeed you could formulate it in terms of something called modules over the group ring. Again, there are lots of ways to formulate it, and some people may have seen more than others of those words that I just said. But this is kind of, I went for the sort of the way that involves the least jargon and just spells out for everybody what it means. Good. Okay, so yeah, one can say it with modules, one can say it with group homomorphisms, one can say it in various different ways. Let's go to examples. So, and I'll go to the case that I'm most interested in. So let's specialize now. So the definition I just gave you was for a general finite group G, but let's go to G being Sn, the symmetric group on the set 1 up to n. Because that's the case we really care about. So I'll talk through some relatively straightforward to say representations of the symmetric group. So actually the first one that's there on the slide now is something that you can do for a general group. I just happen to have done it for the symmetric group. So you can always do this. You could do this for any finite group. What I've done is I've said let my vector space just be the complex numbers. So a one-dimensional vector space over the complex numbers. And take any element of the group and let it act by not changing anything at all. So let it pi v be just equal to v for all permutations in the group, or for all elements in the group if you were doing this for a more general group. So everything is acting trivially. Everything is acting by just fixing things. This, of course, is not a very interesting representation. I mean, the group is not really doing anything at all. But nonetheless, it is an example. So you can easily check that it satisfies, in a fairly trivial kind of way, the list of conditions that I had on the previous slide. So you always have, for any group, a one-dimensional representation called the trivial representation, where all the group elements just fix all the vectors. So that's one thing you could do. It's not telling you anything very interesting. In the case of the symmetric group, there's another one-dimensional thing you can do. This is now specific to the symmetric group. This doesn't happen for all groups, all finite groups. So there's something called the sign representation. So again, as I say, it's going to be one-dimensional. We'll take V to be the vector space C, so a one-dimensional complex vector space. And taking any element, any complex number, what am I going to do? So I think I didn't talk about the sign of a permutation back at the beginning. So I'll remind people about this, but whatever this is, the sign of the permutation pi, it's either +1 or -1. So this action is, the action of a permutation pi is sending a vector to either plus or minus itself. So it's either fixing the copy of C or sending every vector in the complex plane to minus itself. So that's giving a one-dimensional representation. So let me remind you about signs of permutations. So you can always write a permutation as a product of transpositions. So transposition is a little two-cycle. It's a interchange of a pair of elements in the set 1 up to n. And you can express any permutation as a composite of those transpositions, of swaps of two elements. Not uniquely by any means. There will be many, many different ways to write a given permutation as a product of transpositions. But what happens is that when you do that, if you see an even number of transpositions for a given permutation, then however you express it, you'll always see an even number. And similarly, if you see an odd number, however you write it, you will always see an odd number. So the number of transpositions is not invariant for a given permutation, but whether it's even or odd is invariant. And that thing is called the sign. And you assign it to be +1 if it's even and -1 if it's odd. And that thing is called the sign of a permutation. And the properties of sign are exactly kind of what you need for this to be an action. So to check compatibility of the action with the group property, you would need to think about sign of a product. But it is indeed true that the sign of a product is the product of the signs, which is the thing you would need to check that condition. Okay, so in the case of the symmetric group, we have this other one-dimensional representation, the complex numbers with the permutation acting by its sign. And indeed, those are the only two possibilities. That's a fact about representations of the symmetric group. The only one-dimensional ones that you can have are these two, either the trivial one or the sign one. Okay, here's another thing. This is another thing that's specific to the symmetric groups. And this is sort of, it's really bringing in the kind of definition of the symmetric group, or it's defining properties or something. So this is called the natural representation. So what we could do is take a vector space of dimension n and let Sn act by permuting the basis vectors, permuting those n directions that you have in Cn. So if you want to write out what I mean by that, you could write something like this. Here, pi is a permutation in Sn. And remember, our action had to be linear. So once I've told you what to do with the basis elements, everything is determined. So on a linear combination of the basis vectors, well, it has to act linearly. So we just really need to know what happens to each basis vector. And as I said, we're just going to permute the basis vectors using the permutation. So that's a thing that's very specific to the symmetric group. You have this kind of natural action on something n-dimensional because of the definition of the symmetric group as permutations of n things. Okay, and then here's the final representation that I wanted to mention as an example. Here we're actually back to something that works generally for any finite group. So you could, for any finite group, you could talk about its regular representation. I've just written it for the symmetric group. So you take a vector space whose dimension is the size of the group. So here n factorial. And you kind of just write down a basis, a kind of abstract basis, by saying, oh, let there be one basis element, say E sigma, for each sigma in the group. And then you let the action be determined by effectively the action of the group on itself. So you let a permutation pi act on the basis vector associated to another permutation sigma by taking it to the one given by, sort of indexed by the composite of sigma and pi. And we're just using the fact that, you know, effectively the group is acting on itself to do that. So you could do that, as I say, for any finite group. And again, I did a thing I mentioned in the previous case. I mean, I've only specified the action on the basis vectors, but because one of the conditions is that the action has to be linear, everything else is determined once you've specified the action on basis vectors. Okay, so that's going to be my list of examples of representations for the time being, maybe forever. Let me just say a word or two about the word irreducible that came up earlier in connection with these examples. So irreducible was supposed to mean something like you didn't have any smaller representations inside. Which ones of these are irreducible? The first two are. They're one-dimensional, so there's no room for any non-trivial vector subspace inside. So the trivial representation, you have that. That's always an irreducible representation for any group. For sine, you have another one, as I said. Sorry, for the symmetric group, you have sine, which is another one. So we have two different irreducible one-dimensional representations. The natural representation of the symmetric group is not irreducible. We'll actually see a little bit later or in the exercises that it's a sum of two pieces, two irreducible pieces. And that will come up later. And this last one, you might guess it's not going to be irreducible because it's so big. It's got dimension n factorial. That's very far from being irreducible. It has lots and lots of different pieces inside it. And in fact, I'll come back to this later, every single different irreducible lives inside the regular representation. So it's a very big representation containing copies of all the different irreducible ones. Okay, so I'm going to switch tacks a little bit now to go back to some things to do with Young tableau, roughly speaking. And where I'm headed is towards trying to explain something about how, starting from a partition lambda of n and via some tricks involving Young tableau and other things that we've seen already, you can construct an irreducible representation of the symmetric group. And in the end, we'll have seen, at least briefly, how to make all of them. So we'll have made all the basic building blocks of this sort of theory of representations of the symmetric group. So all the basic building blocks for understanding how symmetric groups act on vector spaces. So that's quite ambitious. That's the plan. I mean, it won't be every detail, and certainly when I get to stating results, they'll just be stated. I'm not going to do the proofs, but I want to explain sort of how the story goes. Okay, so switching tack then, I'm going to talk about some things called tabloids. So this is yet another definition related to partitions and tableau. So in order to explain these things called tabloids, I need a new equivalence relation. So it's an equivalence relation on Young tableau of a given shape. So let me just say what I've done. I'm fixing a natural number n, and I'm fixing a shape or a partition lambda, partition of n. And then I'm thinking about Young tableau of that shape. So remember, that's where you put the numbers into the boxes. At the moment, not standard, so no condition, just assign bijectively the numbers to the boxes. So I'm defining two such things to be row equivalent if they've got the same elements in the corresponding rows. So for example, as shown, here we have one where the first row is 1, 2, 3, and this one is equivalent to it because it contains the same numbers 1, 2, 3 in the first row, albeit in a different order, in different boxes. So those two tableaux are row equivalent, and that's a fairly simple idea. You should be able to convince yourselves, I hope, that that's an equivalence relation, right? And that's reasonably straightforward to see. And what a tabloid is an equivalence class. So it's the set of all, so you take one tableau T, and then its equivalence class is the set of all the things that are row equivalent to it. And I'm just going to use a bold kind of T for the corresponding thing. So a little t is going to be a tableau, and the bold one is going to be its equivalence class under this row equivalence relation. For example, so let's just write it out. So if we started with this one, so it's got shape 4, 1, and then we'll take this particular one, which has 1, 2, 3 in the first row in that order, and so on. As above, we'd found another one that was row equivalent, and in this case, here's the full, this list here, the set of those is the full equivalence class under row equivalence of that particular tableau. I mean, so you're allowed to permute the 3 elements in that top row in any possible way. So you're expecting 6 things in that equivalence class, and there's nothing you can do with the 4 because it's just on its own in a row, so you can't permute it with anybody else. So that's all we're expecting, and that's the complete list of all the tableaux that are in that equivalence class. So the set of all those things listed there is a tabloid. And I need a little bit of notation to distinguish a tabloid from the tableau that have gone before. So we'll write tabloids like this. So instead of having boxes, they just have lines separating the rows. And perhaps that notation is sort of reasonably straightforward to remember, perhaps, because we've dropped separating things in a given row in the notation of dropping the vertical lines of the boxes, perhaps to indicate that now, you know, when you do the tabloid thing, it doesn't matter what the position within the row is because they're all equivalent to each other. Let me just check, there's a question, I think. Each tabloid contains exactly one standard tableau. Yes, I think that's right, because, you know, for each row, there'll be exactly one choice where the row is in increasing order. So that's correct, yes. Okay, so that's what tabloids are, these row equivalence classes. And sorry, here we go. What I want to do is explain a kind of recipe for constructing this thing that's called S lambda, and it's the irreducible representation of the symmetric group associated to the partition lambda. So that's what we would like to have our hands on, and this process is supposed to construct all of the irreducible representations of S lambda of the symmetric group for you. Yeah, I think that's right. So there's some responses that say that I got that wrong when I went too fast when I said yes to the previous question. Let me come back to that later. Maybe I think I don't want to spend too long on it now. I think I know what the right thing is to say, but let me pick that up perhaps in tomorrow's Q&A session if it's still a question by then. I think I want to go on now with the construction of these S lambdas. So that what I would like to do is to explain how you get some kind of finite dimensional object on which the symmetric group acts associated to a partition of n. So we start from n, the natural number, and we fix a partition lambda, which is going to give us the shape. And then we just choose a Young tableau of that shape. That's our kind of starting point for the construction. And then, then I'm going to explain this in a little bit more detail on the next slide, but there's going to be associated to that some kind of column group. It's going to be a subgroup of Sn, a collection of permutations forming a subgroup, somehow related to the columns of the tableau. So I'll explain a little bit more, and I'll explain with an example so you'll see what's going on, I hope. And once you've got your hands on that group, what you write down is a signed sum over all the elements of that group. Sign in the sense that came up earlier. So it just means you're going to write down a linear combination of the permutations, and you're going to put a plus in front of the ones that are even and a minus in front of the ones that are odd. Again, example coming very soon. And then what you're going to do is sort of apply that to the tabloid associated to T. So that was that equivalence class thing that we had on the previous slide. So applying this linear combination of permutations is going to give you a linear combination of tabloids. And why are we doing all this? The point is that then we can write down what S lambda is. And it's going to be take complex linear combinations of those things I just said. And there's going to be an action of the symmetric group on those in a reasonably obvious way, just by permuting the entries that you see in the things. And that gives us this irreducible representation that we want. So let's say a tiny bit more about what this really meant, and with an example that might make clearer what's really going on in this construction. So as before, as on the previous slide, natural number n, lambda a partition of n, take a Young tableau T, just pick one of that shape. So the column group that I mentioned, it's the subgroup of Sn that consists of permutations of the entries of the columns. So Ci for column I, and then we're going to put them together in just a second for all the different columns by taking the product over the ones associated to the different columns. Let's do an example, so this might actually become a bit clearer. So here, I guess n was 5. The shape lambda was the partition 3, 2 of 5. Here's a tableau. This is my T here. It's a tableau of that shape. So it's an assignment of the numbers 1, 2, 3, 4, 5 to that shape, to that diagram. And in this case, the column group would be this subgroup of the symmetric group S5 that I've written here. We're allowed to permute the entries within columns. So in the first column, I can obviously do the identity permutation, and I can also swap 1 and 3. And that gives me these two elements here. Similarly, in the second column, well, I could do the identity permutation, or I could swap 2 and 4. And putting those two things together, I could swap both 1 and 3 and 2 and 4 simultaneously. And this gives me this column group for this example, and I hope kind of gets across the idea of what the column group should be in general. And then I said, oh, take the signed sum over the column group. So this is just a formula to record what I already said I meant by that. So it means sum over all the elements of the column group, the permutations in the column group, each one taken with its sign. So this, I don't want to go in too much to where this lives, but think of it as a linear combination of elements of the symmetric group. For example, in the case above, it's just this linear combination. So we've got the 4 permutations that lived in the column group for this particular example. And the ones that are even come with a +1 in front of them in this linear combination. And the ones that are odd come with a -1 in front of them. And we have these 2 single transpositions, so those are odd. the identity element and the product of two transpositions like this, two disjoint transpositions, like that is even. So we get this linear combination. Okay, and then what was the last step? The last step, well, we have to define the E thing, which was applying this thing, this linear combination, this kappa T linear combination. It was applying it to some tabloid. Let's see what that looks like. So finally, we were supposed to apply the kappa to the tabloid associated to T. So this is what it is in the example. So the tableau that we started with had like it was this, except with boxes, not just the horizontal lines, 1, 2, 5 on the first row, and then 3, 4. And then we apply the permutations. And as I said, I haven't written this out explicitly, but the permutations are acting on these things by just in the obvious way, permuting the entries in the tableau or the tabloids or whatever it is we're looking at. So here it's tabloids, and so this is the identity element applied to the tabloid for T. Here the element 1, 3 has been applied, so we've swapped over 1 and 3. Here we've swapped over 2 and 4, and here we've done both of those things simultaneously. So we get a linear combination like that of tabloids. That's what it is for this example. And I mean, that sort of completes the description in some sense, except that we need to look at some examples and try to understand what we're actually saying. So what I've shown you there is, you know, what one of these ET things would look like for a particular T. And then the final step for constructing the S lambda was just take those, all of those, as a basis for, well, for a complex vector space, but that complex vector space then naturally has an action given by the action that we have on the basis elements, as we've just described. And that's giving you some representation of the symmetric group. And, well, there's several claims about that it's irreducible and some other things, which I'll come on to. Let's, before I just sort of say what properties those have, let's go to some examples. Maybe I'll just catch up with questions as well. So I'm going to leave the ones about the precise relationship between the tabloids and the standard tableau. I think we could defer that till tomorrow. Can we use this equivalence relation to prove the Hooke formula? I think my first answer would be I don't know. That might be interesting. I'm not sure I know of a proof along those lines. And then finally, there was a question, is there a name for ET? Well, the general name for things of the form, let me just go back to ET, it would be polytabloid. I mean, a thing of this general type is often called a polytabloid. So that is to say something that's like a linear combination of tabloids of this general sort. So this ET might be called the polytabloid associated to the tableau T or something like that. Okay, so what I want to do, having kind of sketched how you could construct these representations, one for each partition, I want to just sort of go back to some examples and relate them, in some cases, to the examples of representations that I mentioned earlier on. And I'm just going to basically state these because towards the end of the problem sheet, I've put an exercise where I'm checking the details of these things, how they work out for these examples. That's one of the exercises. So let me just say it. So there are cases where we get back some of the examples of representations that I mentioned earlier in the lecture. So if we take this partition, the partition of n, which is just one part, which is all of n, then then the associated representation, if you trace through the details of what I've been doing, is just the trivial representation. So remember, that's a one-dimensional representation on where every element of the group just acts as the identity, doesn't change the vector. This one is not too hard to see. So the shape is, all the boxes, n boxes in a single row. So and then that means that they're all row equivalent to each other. So there's just a single tabloid. They're all in the same equivalence class. There's just one equivalence class. So you can already see it's one-dimensional, and then it's also easy to see that the action is just trivial. So that one's quite straightforward. So we are producing the trivial one-dimensional representation of Sn on this list, and it's associated to the trivial partition, where n is just left on its own as a single part. At the other extreme, in some sense, we can also get the sign representation as an example of this sort. It's at the other extreme in the sense that it's associated to the partition where you split n up as much as possible. So you have n parts, each of which is 1. And again, this one is not too difficult to see. So the shape is that we have n boxes vertically now, so they're all on different rows from each other. So each one is in its own equivalence class. So we've got n factorial different equivalence classes. But on the other hand, the column group is going to be the whole of the symmetric group. And when you do the signed sum over the column group thing, you're going to have just one thing, just one possibility, which is the signed sum over all of them. So you're seeing again that you get something one-dimensional, and with the action this time by sign, because you do the signed sum in the over the column group. So that was a sketch of how that goes for that case. And then here's one more where there's something a bit more going on, and where I won't say very much. I'll leave the details as an exercise. So if you took this partition, so the partition where n minus 1 on the first row and 1 on its own on the next row, then if you trace through the details of what's going on here, you will find that it's an n minus 1 dimensional representation that we've constructed here. And it is irreducible. I mean, kind of the point is that we're constructing irreducible ones. And it's closely related to the natural representation. So remember, that was the n-dimensional thing, where you've got n basis vectors and Sn permuting them in the obvious natural way. So that natural representation is not an irreducible, but it almost is. What it is this irreducible plus a copy of a trivial representation. So it splits into two pieces, an n minus 1 dimensional part, which is associated with this partition I'm talking about here, and plus a copy of the trivial representation. And there's an exercise which kind of explains some steps that you would go through in order to check this statement that I've just made. Okay, so well, that's as much as I'm going to say about the examples for now. So let me just sort of bring things together a bit by explaining how this relates to the standard tableau and the importance of the number of standard tableau of a given shape. So when we constructed this S lambda, I might have skipped over it slightly, but what I didn't say was that the ET things form a basis. What I said was take all complex linear combinations of them. So in other words, take the span of them. And the point is that they're not linearly independent in general. So that's why I didn't say they form a basis, because they don't. And how do you get inside that a good choice of a basis? Well, you take the ones that correspond to standard tableau. So I definitely don't have time to talk about how you prove this, but there's the importance of the standard ones. If you take all of them corresponding to all tableau, you'll get a spanning set for this representation, but you won't get a basis. And a nice way to describe what a choice of basis is to take just the ones that correspond to the standard tableau. And of course, once we know that, if we believe that theorem, then as a corollary, the dimension of the representation is the number of standard tableaux, which is this F lambda that I've been talking about all along, or more or less all along. Let me check the questions quickly. Yeah, so that, I think that's what I just said. So someone is saying, do you take the standard ones because those are independent? Yeah, exactly. So if you take all of them, you'll have lots of linear dependence conditions among them, typically. And the standard condition is guaranteeing linear independence and therefore giving you a basis. That's right. Okay, so then we get, you know, at least I've tried to tell the story of one reason why the F lambdas, the number of standard tableaux, is important. And what I said at the beginning of this lecture was, well, it's important because it's the dimension of some irreducible representation of the symmetric group. And that's kind of where we've got to here. In the last few minutes, I'll just say a few more. I'll do an example first, and then I'll say just a few more sort of general facts that that are relevant from representation theory. Let's do an example first. So let's again pick a very small n, namely 3, and we'll come back to this case that we've looked at several times in examples. So the partition 2, 1, 3, and we've seen before that there are 2 standard tableaux of this shape, namely the ones shown there. So this would be my t, and this would be my t prime. And we can write down the associated tabloids. So for this one, this is t, and here is et. So we write down the tabloid of t first, so that's here. And then we have to do this signed sum over the action of the column group thing. So here the column group for this one contains 1 and 1, 3. So you get the thing itself and the thing that you get when you swap 1 and 3. And for the other one, we start from this standard tableau. This is my t prime, and its associated e is, well, the tabloid of that one. And then we do the signed sum over the column group, and this time the column group contains the identity and the permutation transposing 1 and 2. And so what we see there gives us the et prime. And the point is that what the theory says is that there is a 2-dimensional representation. It says of Sn here, but here n is 3, so that's S3. So there is a 2-dimensional representation of the symmetric group S3. And one way to think about it would be it's the representation which has the basis of consisting of these 2 things that are written here, and with the action of S3 that comes from permuting the entries in these things. Yeah, so that's a really good question. Are all representations some kind of product of these irreducibles? Yeah, they're direct sums is the usual way you would say it. So the usual way you describe the operation of putting representations together would be direct sum, and you're forming kind of direct sum of representations. And yes, every finite dimensional representation is a direct sum of irreducibles. So that's the sense in which they are the basic building blocks, and you can kind of understand all vector spaces with an action, finite dimensional vector spaces with an action, in terms of how it splits up into these irreducible ones. Yeah, absolutely. Okay. So I just wanted to tie a couple of things together and then really summarize to finish off. And I wanted to mention some sort of, so this will be a bit of a whirlwind tour of some basic facts from representation theory and just consequences for the symmetric group to tie things together. So when you have a finite group G, you could ask, well, how many of these basic building blocks of irreducible representations do you have? And it's a basic fact that that is always equal to the number of conjugacy classes inside the group. So remember, we saw that at the beginning. We saw that 2 permutations are conjugate if and only if they have the same cycle type. and we could record the cycle types using partitions. So we had conjugacy classes in bijection with partitions. So the number of irreducible representation is equal to the number of partitions. And well, luckily, what I've just described is how to construct an S lambda, a representation for each partition. And I haven't at all proved it, but in fact, I haven't even really defined properly what irreducible means, but it is a true fact that all these things so constructed are irreducible. So we have an irreducible for each partition, and they're all different from each other. So if we take different partitions, we get non-isomorphic representations. So what we have done is construct all the irreducible representations of the symmetric group, one for each partition. Let me really quickly mention another thing, just because it relates to one of the exercises, and you might have done some computations and wonder why something is happening if you've started looking at the exercises. So here's a general fact from representation theory. If you take the sum, if you take the irreducible representations and think about their dimensions that you get for a general group G, and you sum the square of the dimensions, that will add up to the size of the group. So that's a general fact, and actually it's true for a reason, that the regular representation, which has size the size of the group, I already mentioned that contains every representation, every irreducible, and the number of times it contains it is actually the same as the dimension of the representation. So if you decompose the regular representation in the way that was just suggested by the question, decompose it as a sum of irreducibles, each irreducible is there, and the number of times it's there is equal to its dimension. So a dimension count tells you that the sum of the squares of the dimensions must be equal to the size of the group. And the reason I'm mentioning that mainly is just because I encouraged you on the problem sheet to see some examples of this. So you might have seen, or if you look at the problems, you will see for small n, this instance of this general fact. So if you'd worked out some F lambdas, some examples of F lambdas for all the partitions of n, for small n, and you'd summed their squares, if you'd done all that correctly, what you should have seen is a pattern where the sum of the squares of the F lambdas is equal to n factorial. And that's true because of this. It's a special case of this general fact from representation theory, because we have an irreducible for each lambda, and F lambda is its dimension. So it's the formula at the bottom of the slide is the case for the symmetric group of the formula at the top of the slide. And I'm basically done, but let me just put up one more slide just to summarize everything that's happened here. So what we've seen here is that there's actually a bijection between partitions of n and irreducible representations of Sn. So I showed you how to start from a partition and construct the corresponding representation, and then I've just told you that it's a fact that is indeed irreducible, and they are indeed all different from each other. So that must then be a complete list of all of them. And the importance of the F lambda, the number of standard Young tableaux of shape lambda, was because we've just seen that when you construct this, you get something where there's a basis given, well, in one-to-one correspondence with the standard Young tableau. And so that's the dimension of the associated representation. And I think I've finished there. Maybe I should check the chat for questions. Okay, so let me go back to just check what questions are in the chat. So there's a question about sort of the relationship with character theory, and could you find the number of standard tableau that way? And it mentions the Monaghan-Nakayama rule. I mean, quite possibly, yes, but then in some sense, I mean, that's sort of bringing in technology for which you might already need some of the stuff that I've been discussing. So I think it's sort of, you have to just be careful that it's not something circular where you've kind of already assumed something about the number of standard tableau before you get there. And then, okay, so we can see any finite group as a subgroup of a symmetric group. That's correct. Does this allow us to compute representations for other finite groups too? Or is it not enough? I guess you can definitely get information that way, but I would say that I mean, it might be either not enough or perhaps too much. That is to say, if you have some other group sitting inside the symmetric group, you might, it might not be the most efficient way to try to understand the representation theory of your given group in terms of a large symmetric group that it sits inside. So, for example, if you just take a cyclic group, the complex representations they're all one-dimensional. There are not too many of them. It wouldn't be sensible to try and approach such a question by sitting it inside a big symmetric group and trying to restrict all the representations from the big symmetric group. So the representation theory of groups, it tends to sort of go, there's an aspect of it which goes in families, and there are some families where the theory is quite closely related to, or follows a similar pattern to the kind of thing I've been discussing here, like maybe general linear groups or things like that. And then on the other hand, there are families of groups where the representation theory is actually much simpler than the representation theory of the symmetric group, and it wouldn't make sense really to approach it that way. So I can maybe say more tomorrow if people are interested in that question. I mean, there's quite a lot one could talk about there, and it's bringing in things like restriction of representation. So that's obviously a way of going from a representation of a bigger group to a smaller group, but there are also ways of going the other way, of going from a representation of a subgroup to a bigger group. So there's lots that we could talk about here, and that might be one thing we could do in the session tomorrow. And then there's one short question, maybe I'll make this the last one for now because of time. Someone just asked, what does dimension mean in the last sentence there? So it means dimension of a complex vector space. So representation, remember I said a representation, for me they were all finite dimensional complex vector spaces. And so they have a dimension just in the linear algebra sense of the dimension of the complex vector space. And that's what we were doing here. So here we were taking a basis which corresponded to the standard Young tableau. And we're taking complex linear combinations of those. And so dimension in the sense of complex vector space. So I think perhaps we should stop there for today, but we have a whole hour tomorrow where I'm very happy to take all kinds of questions.
Thank you very much, Sarah. So I thank you for this lecture and for all 4 lectures. So I suggest that we clap our digital hands to thank Sarah for the beautiful course on Young tableau. I will stop recording now.